So now let's try the ultimate game. And the ultimate game is computer programs. So let's say that you take the computer organization class. And in the computer organization class, they'll give you a way of thinking about computers that's perhaps different than the way that normal people do, right? Because what you think about computers and computer organization is that it has a memory, okay? And this is, just a temporary scratch memory. In my personal computer is 8 gigs, okay? We also have some special registers. And some of the registers are data registers. And those are used, for example, that can move value from memory to a register, then add to it, and then take the value from the register back to memory. Okay, they can also be special. And one very special register is the PC, or the program counter. And the program counter tells you where in the memory is the current instruction, or the next instruction that should execute. Okay, so let's see if we can do this with a computer, rather with propositional logic. So 8 gigs. That's in bytes, so that actually means that we have 64 gigs in bits, okay? And so how many propositions do I need? A gig is actually 1,000 megabytes, or 1,000 times a million. So what we have here is 64 times 10 to the 3 times 10 to the 6, or 10 to the 9 propositions. And that is without taking time into account, right? That just simply says, oh, bit such and such is on. We need to be able to talk about the computer at different times. How many different times? I'm going to make a really gross simplification here. I'm going to say that programs take no more than 1,000 steps, okay? Now maybe we need a program that lasts longer than that, so go ahead and choose a maximum. 10 million, cool, right? Whatever you want. So we'll need to do this times time. So we'll end up with 64 times 10 to the 3 times 10 to the 6 times 10 to the 3 times 10 to the 12th, basically 64 times 10 to the 12th, or 6 times 10 to the 13th. That's a big number, okay? But those are all the propositions that we need for the memory, okay? Now what about the registers? Well, the good news is that there's not as many registers, right? Registers are basically memory that is really, really, really fast. So it's very expensive. We just don't have as much of it. Let's say that I need, let's just be gross, 10,000 bits, okay? And then times 1,000 time, and we'll end up with, 10 million propositions. That's nothing compared to the 64 times 10 to the 12th. So okay, so we have a lot of bits, right? So what does this let us do? This lets us describe the computer at an instant. Okay, good. So that's our description of the board, right? What else do we need? We need an initial configuration. And what might the initial configuration look like? Well, up to this point, we've always said, oh, the board is empty. That's not quite true for computers. For one thing, you need your program that you want to run to be stored in memory. So you will have to say things like this. This particular bit location has a 1, this one has a 0, this one has a 0. And what you're saying is describing your program, right? That might have been an if statement. The other thing you need to do is the program counter needs to be pointing at that location, right? So we need to say what the program counter is. And we could just say that all of the variables are initialized at 0, okay? Although we may need, for example, your program says int x equals 1, so that one needs to be 1. But all that is easy to take care of. There's a lot of things to write. I mean, this is an awful lot of propositions, but it's conceptually simple. So this can be done, and we have the initial configuration. Okay. Now we need to describe the evolution of the system, right? The legal evolution of the system. And what does that mean? I need to have instructions, or rather expressions, propositional expressions, that will let me say this. Suppose that the program counter has this value. And when I look at that particular memory location, I find this instruction, right? Then at the next time step, that instruction will have taken place. Let's pick a really simple instruction. Let's say the instruction that says increment register A, right? So we would say, oh, the program counter You can't really say had disposition when you have to say the program counter, the first bit is 0, the second bit is 1, the third bit is 0, the fourth bit is 0, the fifth bit is 1, and so on, right? And that then points to a particular thing. And that's propositional. And then we say, and at that time in that memory location, so we now say bit such and such in the memory at that time is equal to 0, and bit such and such is equal to 1, and bit such and such is equal to 0. And that is simply describing the instruction increment A, okay, register A. And at that time, register A, the first bit is 0, the second bit is 0, the third bit is 1, the fourth bit is 1, and so on, whatever it is. Well, that should imply that at time, let's say we started at 7, so at time 8, register A is going to have, well, the first bit is 0, the second bit is 0, and so on, right? Each one of those is just a proposition. And we have to take care of what's usually called the framing problem, which is nothing else changed, okay? Can we do that? Yes, we can. Yes, we can, although, you know what? I'm a computer scientist. I would simply not do that. What I would do is I would write a program that would spit all those things out. But yes, we can write the evolution, okay? What about picking a winner, okay? So the end. Yes, we can do that. And the way we do it is similar to what we just did. The program counter has this particular bits in it, and the corresponding memory location is the instruction that stands for halt. In that case, at the next time step, the game is over. I mean, the computation is finished. So as long as we don't have to go more than 1,000 steps, because you see, for every step, we need to have more and more of these rules, right? So to have a fixed set of rules, we need to be able to fix the number of steps beforehand. As long as there are no more than 1,000 steps, then yes, I can actually represent a program, in fact, an entire computer, using propositional logic. 2,000 steps, no problem. 10,000 steps, no problem. 1 Google steps, no problem, okay? You just have to pick ahead of time. The only thing you can tell me is, my program will run, I promise it's going to stop, but I don't know when. Sorry, no good, okay? It needs to have a maximum bound. We'll go back to that. That's a really important point I want you to get. But look, how powerful is propositional logic? If you have any program that you can think of where you can tell me how long that program will take to execute, we can model it in propositional logic.